All right, so we're looking at some basic stoichiometry conversions, and we are in Berkeley Review Chemistry 1 in the stoichiometry section, which is section 1, and we're looking specifically at question 36. So we want to determine the final chloride ion concentration when we mix 50 mils of 0.25 molar HCl with 25 mils of 0.5 molar NaOH. So we're going to do, so we kind of see both things that are going on. We have 50 milliliters of a 0.25 molar solution, but 0.25 molar could be 0.25 moles per liter. It could also be 0.25 millimoles per milliliter. This gives me the number of millimoles of HCl, and I know for every 1 millimole of HCl, there is also 1 millimole of Cl minus. $50 times 0.25 is 50 divided by 4. 50 divided by 2 is 25, and 25 divided by 2 is 12.5. So I have 12.5 millimoles of Cl minus. Now, of course, I don't have any Cl minus in the other solution. What that does, however, is it adds volume. The first solution, I had 50 mils. The second solution, I have 25 mils. We always assume these volumes are additive, therefore 75 milliliters. Notice that millimoles per milliliter is molarity, so I don't have to convert at all. So rather than converting this to liters and then converting this back, I don't have to convert at all. So 12.5 over 75, let's think about estimating that. 25 over 75 is pretty easy. That's 1/3. 12 and a half is half of 25. So I have 1/2 of 1/3. That is 1/6, which is 0.166. Repeating, you could estimate that as 0.17, and that is precisely answer choice C. Now, this is a good time to talk about some fractions just in estimating. Let's talk about 1/2. Let's talk about 1/3. Let's talk about 1/4, 1/6, 1/7, 1/8, 1/9. Let's also talk about 1/11. Of course, 1/10 is just going to be 0.1. This will be 0.5, 0.33 repeating, 0.25, 1/6 is 0.16 repeating, 1/7 is 0.142, 1/8 is 0.125. Now 1/9 are pretty interesting. You just repeat whatever is in the top. So 1/9 is 0.111, 2/9 is 0.222, etc. And 11ths is going to be 0.09 repeating. So 2/11ths will be 0.18 repeating. 3/11ths will be 0.27 repeating. These are really good markers so that you can easily estimate mathematical solutions. Okay, so we're looking at passage 7, which deals with solution chemistry. So my advice would be not to spend any time interpreting the passage. You see a lot of definitions. I would immediately go to questions because this is data, and you can always look at the data anytime you wish. So let's look at question 41. Adding water to an aqueous solution of known concentration decreases all of the following except. All right, let's think about some definitions here. Density is mass per unit volume. This certainly is going to increase the denominator without increasing the numerator. So density definitely goes down. That means I can eliminate, and let me just show you how I want you to think about this. Because if you approach every question like this, this is how you're going to take your test. When I first started taking an Mcat, I always looked for the perfect answer, and that was a very bad move. Once I started doing it this way, the number of questions I missed went down substantively. So we know that A is going to decrease. We're looking for the one that doesn't decrease. That means A should be eliminated. I'm just going to put a line right through it and not consider it. Molarity. Moles of solute over liters of solution. All right. I'm going to increase the volume, which means I'm going to decrease the molarity. It's going to become more dilute. So B should be eliminated. We look at C. Molality. Well, molality is moles of solute over kilogram of solvent. Now, that's mass, but I'm adding more volume, which means I'm adding more mass. This should also go down. So look, I feel very confident about those three eliminations. I'm going to choose D. And again, the reason I'm going to choose D is that I'm most confident that A, B, and C would be altered by adding water to an aqueous solution. Now, so this is interesting because Berkeley Review tells us that the credited response is A, and I got an issue with this, and I want to explain why I do not believe A is a good answer. We have a solution that has a known concentration. So unless this is a pure substance, the density will change when you dilute it. Has to. If it is a pure substance, the wording of the question is very ambiguous, so I would approach this cautiously. Now, being fair and looking at D, the mass percent of the solute is going to change as well because less of your solution is going to be solute and more of it will be solvent. Just something to keep in mind. Usually on the Mcat you don't get such a vaguely stated question. Let's go ahead and move on to number 42. One gram of a salt is just 1 grams of a salt. That's just poor English. That's terrible. Dissolved into 100 mils of water, the volume of the solution is greater than 100 mil, but less than 101 mil. What can be said about the concentration of the solution? Well, we know that the density of the water is greater than 1. So I guess what we should do is just plug in a couple of numbers here. Let's say we have 1.0 grams of a salt. Let's pick something real easy. Let's pick NaCl. NaCl has a mass of 58.5 grams per mole. And we're going to place this in 100 grams of solvent. So this would be 1 divided by 58.5 divided by 0.1 kilograms. That's equal to my molality. Or if you prefer, 10 over 58.5, which is about 0.18 molal. What would the molarity be? It would be moles, which is 1 over 58.5, over volume, which would be 0.1005 liters. Remember, they said that it's greater than 100 mils, but less than 101. So I just took the middle, 100.5. So when I divide by a larger number, 0.1005 is larger than 0.1, this number will be smaller, which means molality must be greater than molarity. So we can eliminate B, we can eliminate D. And C is not true. The density of the solution isn't less than that of pure water, it's more. So I would go with A. And what do our magical people tell us the answer is? They'll tell us it's A. Good. About time they came around. All right. Number 43. Organic compound with a density that is less than 1 gram per mil is added to an organic liquid, also with a density that is less than 1 gram per mil. What can be said about the concentration of the solution? So again, we're comparing molarity to molality, but the density is going to be less than 1. Let's think about this for a moment. So let's say that the density is 0.9 grams per milliliter. And we are adding let's say we add 1 mole. So for molality, all I care about is mass. And let's say that I add 10 milliliters. Well, that's going to be 9 grams, which is 0.009 kilograms. For molarity, 1 mole, 10 milliliters, which is going to be 0.010 liters. Which one is larger? It's going to be the molality again, right? Molality is greater than molarity. There's no way you can determine which of those two solutions has the greater density. You just know they're both less than 1. So get rid of A, get rid of B, and let's go with C. Molality should be greater. So that is response C on the answers. If we look at the answer choices, we can't determine the relative densities of the two components, so automatically A and B are gone, and we've already demonstrated that molality is greater than molarity, so D is gone. That leaves C as the best answer. All right, number 44. Given that a solute is denser than the solvent into which it dissolves, what is true of the concentration measurements of different solutions made up solely of the two components? The solute is denser. Well, let's think about density for just a minute. Density is going to be mass over volume. So if I have density of A is greater than density of B, that means if I take equal molar volumes, the mass of A will be greater than the mass of B because there's a greater density. So let's read the question carefully. It's a little convoluted, and I'm not entirely convinced that this is a great Mcat question. Mcat is really not in the business of giving you stoichiometric passages. I think what they're trying to do here is to get you well grounded in thinking about concentration units. That could be a discrete question or part of another passage. You're not going to see a passage like this. Okay, the solution with the greatest density also has the greatest molarity and molality. Now, I'll buy this. The solution with the greatest density. Let's think about a situation where we have three grams of a solute, and let's say, just to be simple, let's say its molar mass is 30. So that's 0.1 moles. And let's say that we have 10 grams, which is 0.01 kilograms. So we have 10 grams of solvent. And then let's do another one where we have 6 grams. And we also have 10 grams of solvent. So in this case, we would have 0.2 divided by 0.01. Clearly the molality increases, right? So we can't eliminate A yet. We can eliminate B. We can eliminate C. We can eliminate D. It's got to be A. Is that what the magic people said? Mm-hmm. Good. So I like the idea of taking a number, evaluating it, and then it deconvolutes the question. A lot of times people get so wrapped up in how it's worded and it's confusing that they don't think clearly, and we want to prevent that. Okay, now this is a nice Mcat question. Basic math question. How many mils of pure water must be added to 100 mils of 0.25 molar KBr to dilute it to 0.1? Be careful here. All right. Now, and it doesn't look like they're really trying to trick us up a whole lot. So, here's how I do this. If I'm going from 0.25 molar to 0.1 molar, I need to dilute by a factor of 2.5. This is 2.5 times more dilute than this, which means I need 2.5 times more volume, which would be 250 mils. That's what I need the final volume to be. Now notice what they do here. They throw that at you. But you already have 100. I need to add 150. Now, if that bothers you, let me show you another way you can do it. You can do the old familiar M1 V1 equals M2 V2, which is what I just did, by the way. Because we have 100 mils, I would not convert. Converting is for suckers, especially when there's no reason that you need to. 0.25 molar equals 0.1 molar. That's my final volume. 100 times 0.25 divided by 0.1 is 250 mils. But I must subtract the 100 I already have. Because the question is, how much do I add? Make sure you read the question carefully. Therein lies the lesson. So when we evaluate our responses, C is the best answer for number 45. Okay. To achieve the same chloride ion concentration as 1 gram of NaCl, of course the molar mass is 50. That's 58.453. You got to round up to 0.5. People, come on. Grams per mole, that equals number of moles, right? Dissolved into 100 ml solution. So let's divide this by 0.1 liters. That's just 10 over 58.4. And there's only one Cl, right? So this is going to be about 0.18. That's about what it's going to be. So how many grams of MgCl2 do I need so that I get this concentration? So honestly, what I would do is just look at these mathematically and see which one is about 2/10. First of all, this is 1/2. This is about 1/2. That's not a bad answer choice. This one is going to be a problem. That's greater than 1. So let's get rid of B. And, you know, this estimating is really an art. So let me not just take that for granted. So we just decided that it would be, that our answer, given this, should be 10 over 58.4 when we simplified what's up here. So that's 1 divided by 58.4 divided by 0.1. That's the same as multiplying the numerator. Dividing the numerator by 1/10 is the same as multiplying. Dividing by 1/10 is the same as multiplying by 10. So when I look at this guy right here, this is 58.4 over 185.8. Okay. Now that's ambiguous, so we'll think about that one. This one is not ambiguous. This is 116.8 over 94.9. That's BS. So my favorite thing to do. And really, I like doing this on the Mcat because you get to say, screw you, I'm not picking that one. You don't get me this time. I mean, emotionally, that's very powerful when you can do that. Now, what's the difference between A and C? Is they've been flipped, haven't they? C sucks as well. Because when I evaluate C, that's 94.9 over 116.8. There's no way that's this number. Because if I multiply this by 2, I get the same denominator, right? 116.8. I can do that as long as I multiply the top. 20 over 116.8 is not the same as 94.9. So, see ya, turkey. Now, what about D? D's even worse. I think A is the one that I want. What do the magic people say?
They said C. I said A.
Really?
Mm-hmm. They said C. It must be a typo. Can't be.
That's pretty silly. Okay, so let's look at this a little bit more carefully. Let's actually do the dimensional analysis. The math doesn't add up. Their math doesn't add up.
I think that's one I have.
But let's not take it for granted. Maybe we made a false assumption. So let's just do it this way. I want 1 gram of Cl minus. In 0.1 liters of solution. I know that there are 35.45 grams of Cl minus in 1 mole of Cl minus. I know that there are 2 moles of Cl minus in 1 mole of MgCl2. I know that 1 mole of MgCl2 is 94.9 grams of MgCl2. And that would tell me how much MgCl2 I needed to add. The problem with that now is that you have this. Now, if we go 1 gram of NaCl, well, actually, you know what? Let me pull that back just a minute. I think I do agree that it might be C. Let's do this. Do we want the same as 1 gram of NaCl? And really the volume is irrelevant because the volume's not going to change. I know that there's 58.4 grams of NaCl in 1 mole of NaCl. 1 mole of NaCl gives me 1 mole of Cl minus. There are 2 moles of Cl minus in 1 mole of MgCl2. And for every 1 mole of MgCl2, there's 94.9 grams. Now let's just get rid of all the ones here to simplify this. What do we have? We have 94.9. Thing is not writing as well as I wanted to. Let's go blue. 94.9 divided by 58.4 times 1/2. times 1. There it is. Now, to me, the mistake I must have made is in the beginning. So 1 gram of NaCl, 58.4 grams in 1 mole. Of NaCl. One over 58.4 moles of Cl minus. If we come over here and look at C, because this should add up when we do this. And it still doesn't add up. That doesn't make any sense. We need to let go of that. I guess the long dimensional analysis is the way to go. That's interesting. All right, last one. Given 2 compounds, A and B, the fact that B has a higher molar mass than A, but A is denser than B, which of the following mixtures would have the greatest mole fraction of A? All right, so when we do mole fraction, mole fraction of A is equal to the moles of A over the total moles, which would be the moles of A plus the moles of B. It's sometimes called a mole percent. Where did you take your Gen Chem?
Southwest.
Yeah, that's part of the problem. Who'd you have? Darnell, Whaley.
You know that was in the 90s, right?
That's been that long?
Mm-hmm.
Woman, you got guts.
Why you say that? I
Not
have.
a lot of people that would be trying to do what you're doing. Just to be respected.
Nelson told me I need to go and audit a physics and a chemistry course.
He told you that? If he tells you to do something, you do it. Because he'll write it down. And if you don't do it, he'll blackball you. So, do it. I'm teaching Orgo 1 and 2 in the summer. You probably need Gen Chem, though. Sure, we can figure something out. All right, so B has the higher molar mass. Okay, so let's say B is 40 grams per mole and A is 30 grams per mole. But A is denser than B. So let's say this is 30 grams in 100 mils of solution. And let's say this is 40 in 200 mils of solution. Which of the following will have the greatest mole fraction of A? Okay, think about this. The smaller the molecular weight, the greater the fraction of a mole. So if I take 1 gram of A, that means I have 1/30th of a mole. And if I take 1 gram of B, that means I have 1/40th of a mole. The mole fraction of A is going to be 1/30th over 1/40th plus 1/30th. A's got to be right.
See why I struggle.
Well, I guess we can't. What we have to do is we have to take into account the volume as well. That is, they're getting very devilish on this. So, and I don't like the fact they're calling it compound A and compound B. They should call it solution A and solution B. Again, their wording is very misleading. I would stand by A would work. So let's take into account that it's a solution now. If you take 1 mil, well, C definitely works because not only do you have the smaller molecular weight, but you're taking a larger mass of the compound. C is the best answer, but A also works. Okay, let's put this one to bed now.